Thank you very much. Thank you for the introduction. And thank you for inviting me to this seminar. I hope you can see my screen well. And this talk, as you mentioned, will be slightly different than those usually done in this seminar, in the sense that I will not present a particular research topic, but I will focus on a very potent tool that could allow you to potentially greatly increase the effectiveness of your imaging in photothermal spectroscopy and imaging. Of course, this talk will relate to the previous one quite well in terms of pump probe imaging in the wish to do Raman spectroscopy or contrast imaging, phase contrast imaging. And I will follow the following agenda. First, I will introduce Heliotis very briefly and talk quickly about the C4 camera, what it is, what it does. And then we will go into the depths of the principle and how the camera actually works, followed by the presentation of a couple of examples and, of course, a Q&A session. So Heliotis is a company in Switzerland, which is that small dot on the map. But it's a fairly large company nowadays, and it is specialized in high precision 3D metrology and optical locking technology. And what I mean by that is that the core competence of Heliotis is basically the development of a highly specialized CMOS sensor, which has the particularity that every single pixel of the sensor does a very nice demodulation operation. So we have 1 million lock-in amplifiers in a pixel, basically. What can we do with that? Well, for example, if we expose it to modulate light coming from an interferometer, then we can build a device that is very capable of measuring nanometer scaled objects in 3D. This is
Istvan, your sound falls out from time to time. I don't.
Can you hear me again?
Now we can hear you, but there are some interruptions. So maybe I can
you hear?
sign.
Can you see the slides as well?
Yeah, the slides are perfect, but the sound is sometimes interrupted. I think it's working now.
Excellent. So another thing that you can do with this technology is you can put it into a camera, and this is the heliCam C4 locking camera. And this opens the opportunity for new applications. And this is where your expertise comes in, and our confidence that this can be a very useful tool for you. In order to facilitate research, basically, Heliotis has an in-house research team. And we can also do combined projects like EU projects or InnoSwiss projects in order to have a nice collaboration. So what is lock-in demodulation and how it works? I will be very brief in this because I think you're quite familiar with this. So let's assume that you have some sort of periodic excitation. Let's say a laser shining at an object, and that object responds, let's say, with a fluorescent image, which is shown on the lower image. And let's say that this response is embedded in quite a lot of DC background and noise. And what you'd like to recover is obviously the magnitude and the phase of this response. And this is done typically with a photodiode, an electronic lock-in amplifier, and then some sort of post-processing on the PC, which gives you your desired result. However, you could also use the Heliotis sensor, which does this in the pixel with analog electronics, actually. And let's see what the individual stages are and how the sensor does this. So first of all, light detection is done very similar to standard sensors with a photosensitive element in the CMOS sensor, and of course photoelectrons are accumulated and then read out. However, already at this point, Heliotis has a certain distinction. We have a feature which allows the attenuation of the photoelectron accumulation, actually. So this is in order to prevent the saturation of a pixel as it would occur normally in a camera. And this literally happens live while the acquisition is happening. So this brings down your response signal to something that is manageable and would have otherwise long saturated your camera. The technology is CMOS based, so this means that the best quantum efficiency is obviously in the visible range, but both quantum efficiency ranges and sensitivity could potentially be enhanced by, for example, a photon multiplier. So the next step is the mixing bit in the demodulation process. And once again, let's assume that this here is your response signal, and you provide a reference, demodulation reference signal. And in fact, the Heliotis sensor uses this reference signal and a 90-degree shifted version of it. Now, if you want to do demodulation in a million parallel lines and you want to do it quickly, you need to do some sort of simplification. So it turns out that you can very fairly approximate this reference signal with a set of square pulses, where the square pulses can be positive and negative. They have a magnitude of 1 or -1 or 0. So if you multiply the two signals, what you will get are basically 4 values per period of the signal. And now, does this remind you a little bit of imaging? I hope it does, because this is precisely what is happening. The camera does one image in every quarter period and then uses pairwise subtraction in order to calculate your in-quarter and quadrature signals for that particular period. So can you do the same with the regular camera? And the answer is, of course, yes, you could, but there are a couple of things that you have to consider. The first is the data rate that you're going to generate, which you have to transfer somehow to the PC and process, but also the inherent frame rate limitation of regular 2D cameras, which is far below the rate that we can achieve. And of course, the light limitation, the DC light limitation of a DC camera. So in comparison, the heliCam can demodulate at 250 kilohertz, which would be the literal equivalent of 1 million images a second acquired with the regular camera. The next step is the filtering process. And as you may know, this is the application of a boxcar filter onto the previously calculated signal, basically a convolution. And the length of this boxcar filter is basically an integer multiple of your the number of periods of a period length. So for example, you could integrate over 20 periods. In analog electronics, this actually means a summation. So you take all your period-wise I and Q signals and you integrate them up. And this is what we call a frame. So there are a couple of consequences to this. Obviously, this is a low-pass filter, so high-frequency noise gets eliminated. There is quite a lot of signal accumulation, so you boost your signal-to-noise ratio very considerably. The whole thing is done on the chip, so you don't have to worry about the process itself, and only frame-level information ever leaves the camera. So multiple such frames are accumulated in a volume, which you can then receive on the PC. So that the amount of shear data reduction is illustrated here. Basically, this first bit is done in electronics on a pixel level. So we go on pixel level from about 1 million images a second to, in this particular example, 5,000 images a second, which is then passed to an FPGA for post-processing. And for example, this post-processing can be the calculation of magnitude and phase response. And then this is streamed out to a computer. So demodulation is very nice, but synchronization is everything. And you know this certainly from your experiments. And in order to facilitate this, the heliCam can be used in 2 modes. So it can be used as a slave, where you can feed in reference signals to the camera. As such, you can feed in 1 TTL pulse that starts the recording. So it acts as a phase synchronization, a phase locking. And then you can feed in a pulse, which actually controls the demodulation period, or you can even control individual quarter times of the demodulation with this. Alternatively, you can use the heliCam as a master, and then you obtain a TTL pulse, which is corresponding to the effectively used demodulation reference. There are several variants of the sensor, and I will not go into the detail. The idea behind this is that we can offer pretty much one type of sensor for every kind of application. And this is something that we would discuss before you can start working with such a sensor. The interface is standardized, and we follow very strictly the heliCam implementation, the heliCam standards guidelines for implementation, and we have an SDK for multiple programming languages. So where is the camera used? And the first outlook shows you the camera is used pretty much worldwide, and we are very keen on extending this map. And the second image shows you the application areas where you can see that it's used quite widely. And the usage goes from literally velocimetry towards pump probe experiments, towards spectroscopy, especially Raman spectroscopy, imaging, three-dimensional imaging with interferometry, and NV magnetometry, which is a very recent topic, and it's growing really rapidly. And then, of course, interaction of light and scattering media, which might link very nicely to the previous talk as well. And in this sense, the explicit goal of today's presentation and our wish is to promote this camera in photothermal microscopy and spectroscopy. Heliotis, of course, supports both basic research, and if you have an idea towards a commercial application, we are, of course, very keen to go with that as well and help you realize that. Our first application example is basically Raman spectroscopy, and it's based on the paper that you can see below here. And as you may know, Raman spectroscopy is very much appreciated as a very nice method to do label-free chemical detection. However, Raman spectroscopy has the tricky characteristic that it is a very small signal which is sitting on top of a very large and noisy background. So for this reason, historically, it was actually fairly difficult to detect it. And it can be done very nicely with heliCam. And an example is shown here, where basically a light source with a slightly shifted frequency, or alternatively, two light sources with slightly alternated frequencies are used to illuminate a sample, and the response is spread with a spectrograph, and you can see the Raman shift corresponding to the excitation shift. And now the heliCam comes into play. And with the heliCam, you can, first of all, eliminate the large background. Second of all, eliminate the rest of the background through differential imaging. Boost your signal to noise ratio due to signal accumulation, due to the integration process, and do differential spectral imaging in one shot. There are several versions of this experiment explained in this paper, and I invite you to have a closer look if you're interested. I'm only going to show two versions. The first version uses a single laser, and this experiment is aimed at recovering one true Raman spectrum, not differentially, but a single individual spectrum. And as you can see in the results, the locked-in camera managed to recover this Raman spectrum very nicely that would otherwise be suppressed in noise with a standard camera setup. This improves the signal to noise ratio quite considerably. And I need to tell you that this experiment was done with an older version of the camera, and what the authors did is they accounted for a longer exposure time by averaging over the number of frames that they got in the output. With the newer version of the camera, there is far more leeway to extend the exposure time. Hence, you could achieve such a dramatic boost in signal-to-noise ratio even with that. And in addition, you could still average over the number of frames that you record. So here we see easily a 5 times improvement of signal-to-noise ratio. To the second part, which is even more complex, we use a second laser, and with that second laser, we actually do differential Raman imaging. So what you see here is now the difference in the phase shift in the spectrum shift of the Raman response, and we can see that in a similar way, signal-to-noise ratio can be boosted quite nicely. A second application is in the field of magnetometry, and this is done with diamond NV defects, which is a very sharply rising topic. And just to briefly explain what happens here is basically in a diamond lattice, one can replace the carbon atoms with a nitrogen and a vacancy. This structure has now a very nice feature, and that is that it has a spin-dependent photoluminescence. So one can excite this with a green laser and it responds with red fluorescence. And the particularity is that this structure can be in a spin state 0 or in a spin state ±1. And the spin state 0 will result in a much more intense luminescence than the spin state ±1.
Istvan, about 3 minutes left.
Yes, thank you. So what happens now if you expose this structure to a magnetic field? Obviously, it splits the spin states into +1 and -1 respectively. And it does so depending on the strength of the magnetic field that is being applied. Hence, it can be used as a sensor for such a magnetic field. But how do you realize the population transition? And the answer is by microwave resonance. So you sweep the microwave spectrum, and by imaging, you read out the response, and you figure out where the resonance frequencies are. Now you can lock in at one resonant microwave frequency, and you can modulate your magnetic field. And from the optical response, it is possible to calculate the strength of the magnetic field quite nicely and actually do imaging with this technique. So this is the setup that the group shown in the paper below has done. And they have imaged a microcoil with this technique. So first they swept the microwave spectrum, they identified the peaks, and they've done so with differential imaging with the heliCam. And then they fixed the magnetic field and they started to modulate the current that is flowing through the microcoil. Hence, the magnetic field was altered, and they could indeed very nicely image this microcoil. Another application is in white light interferometry, and this is what also Heliotis is doing. Basically, this is a standard interferometric setup, with the exception that we use a broader light source, and we move the interferometer relative to the sample. So we alter the path length of between reference path and sample path. And as a response, we get a very nicely modulated interferometric signal, which is then captured by the sensor and is being decoded, resulting in a nice 3D surface. And the potential of this technology, when applied in the phase imaging mode, is that it can measure up to a few nanometers in surface differences. This particularly is a nanowire deposited with atomic layer deposition onto a piece of glass. So in a summary, what I can say is that I have shown you the application of the heliCam in different fields where I was highlighting the benefits of using such a camera, which would be to speed up the process that you're trying to demodulate, reduce the data very significantly, and also suppress the background. And due to the similarity of the talks that we have heard in this very nice seminar, we believe that the same principle can be applied quite nicely in photothermal imaging as well. So with this being said, I'm very, very curious about your ideas and looking forward to questions and comments. Thank you very much.
Thank you very much. It's a very exciting talk. Are there questions or remarks? Maybe I can start with one while people are thinking or writing in the chat. One of the advantages of CCDs is that you have counts, right? You get for each photon, or sometimes for a given number of photons, counts, so that this suppresses a lot of the noise that you would get from electronics, amplifiers, etc. And so what I don't know, because you didn't tell much about the true mechanism of the camera. I suppose this is proprietary, but still you can maybe tell us whether we keep this advantage. I mean, if you have to go to very weak signals, right, can you still do the modulation while keeping the the digital character of photon counting, or is that lost in some sort of analog signal that then will be sort of subject to all the imperfections of analog treatment of the signal?
Very good question. And the answer, it depends on the domain that you're using the camera in. So what the heliCam is not, it is not a super low light camera. It is not a super sensitive camera, but in fact, the typical full west that we are using are substantially larger than those cameras. And also the readout noise of the heliCam is bigger than those cameras. Okay. What I'm trying to say is that for the heliCam, you need more light than you would have in an ultra low overall light setup. But if you do have this more light, then you can decode a much smaller modulation on a much bigger background. Basically, there are two kinds of noise that can appear, and that is photon shot noise, and that is what you were talking about, I believe. And there is, of course, digital readout noise. The application type, the amount of light decides in which regime you are. And typically, you could say that that readout noise would be the equivalent of 1,000 to 2,000 photoelectrons in a pretty generic setup, while you would expect a shot noise an order of magnitude bigger. So it should, the readout procedure and the analog processing should in fact not disturb you, it should actually help you.
All right, so definitely for photothermal, this is, usually you have a large background, so this is not the problem, that the signals are not that very weak, and you want to extract the weak signal from that large background.
Exactly.
Thank you very much. Are there more questions? I don't see any hands raised. No. Any more questions for Istvan? No, I'm afraid not. So I think I will. Yes, Paula, please. Yes, go ahead.
Yes. So did I get correctly that the maximum modulation frequency that one can use with this camera is 250 kilohertz?
Yes, that would be the maximum demodulation frequency.
Okay. Because for a number of applications, it would be good to be able to go to higher frequencies, more like in the megahertz range. So is this a fundamental limitation? Will you think one could potentially go to megahertz?
It is a limitation of what electronics is capable to do. So it would be very difficult to go higher. As a matter of fact, the issue is going higher with such number of pixels. And typically the demand is for more pixels. So it is in this direction where the technology extends to. However, you could think of possibly using a couple of experimental tricks to alleviate this. So perhaps you do not want to have your response in a single period of the demodulation. You could spread your response if it was, for example, pretty even, and you could accumulate several responses within even one period of demodulation.
Mm-hmm.
You would just somehow modulate the response. So let's say that you have 100 responses in the first quarter period, 100 in the second, but then none in the third and none in the fourth quarter. So by this little trick, you would use the first quarter to already record 1,000 responses.
Okay, I see. Okay, good. Thank you.